So welcome to this lecture on further studies after the previous lecture on the 1D Liang's impedance model. Now in today's talk we'll do two things. Number one, we will introduce you to 2D model. We'll not go into the derivation. And number two, we'll introduce you to impedance-based identification and structural health monitoring. So we begin with recapitulation. In the previous class we had derived this equation based on 2D impedance model, and we saw that this equation has two components. One component is this part together with this. So this is supposed to be the capacitive part. Why? It is neutral because it does not have any component of the structure. Structure component makes its appearance in the other part in terms of the impedance Z. So this impedance Z of the structure, that holds key to damage detection in the EMI technique. If there is any damage, then Z undergoes change, and this change is reflected as change in the signature Y. So this 1D model, we have done its very thorough derivation. So I hope that each one of you have individually derived the expression. Now let's see the typical characteristics of the two components G and V. So if we see G and V, typically they would be like this. The appearance would be like this. What we can do is that we can see G individually. So what we can find here, we find here peaks in the signature of the real part. So one thing is for sure, that it has a fixed slope, a baseline kind of thing, and then there are peaks. Similarly, if we see the imaginary part also has a fixed slope, and then it also has peaks. So these peaks are a little bit different from the corresponding peaks of the real part. So these appear at the same frequencies as for the real part, but there is a difference here, that the peaks are in the form of a kink. Kink is something like this. It goes up, then goes down, and like this in the case of the imaginary part. Whereas in the case of the real part, G, we have very sharp and straightforward peaks. Now it can be shown that if the mechanical impedance of the structure is very large as compared to the mechanical impedance of the piezoelectric patch, then the peaks, they would only reflect to the structure resonance peak. They will correspond to the resonance frequencies of the structure. But if it happens that the mechanical impedance of the structure and the mechanical impedance of the patch, they are of the same order of magnitude, then we will find that both of them will contribute to the peaks. So here we see in detail again. Now we use log scale here. So it appears as if that the B part, there is no peak at all. So this is an important point to note, that whereas the peaks are very sharp in the case of the real part, they are not there so sharp in the imaginary part. And this has a reason, which in fact we can very easily find out. So if we now list the observations, we find three main observations. First observation is that the magnitude of the imaginary part B is several times that of the real part G, which we can see at least one order of magnitude, 110 magnitude difference is there between B and G. We can see from either the log scale plot or the main plot. It's more clear from the log scale plot. So the imaginary part is largely straight line, peaks are less dominant. And number 3, both the real part G and the imaginary part B, they exhibit linear variation with frequency, and more so in the case of the imaginary part P. So we'll see why these things are happening with using the Liang's equation we have already. So let's look at the equation derived by Liang. So here what we can find is, let's just recapitulate one by one. So here what is omega? Omega is the frequency, W, L, H, they are the dimensions of the patch, epsilon 33 with superscript T, this is the electric permittivity of the PZ material. What does T indicate in the superscript? T indicates that this quantity is measured at constant stress. And similarly, the bar above epsilon 33, it indicates that this is a dynamic parameter. Similarly, Z is the mechanical impedance of the PZT patch, Z is the mechanical impedance of the structure, D31 is piezoelectric strain coefficient, Y, E and bar on the top is the Young's modulus of elasticity of the PZT material. What does E indicate here? E indicate that it is measured at 0 electric field. Now kappa tan KL by KL, so this is the wave number and L is the half length of the patch. So this is the equation. So what we find here, that if we see these two parts, then they are like independent of the structure, epsilon 33 T bar and D31 square Y, they are sort of inert and they make up the capacitive component largely, and the structure part appears here in the form of the Z. So this part, it is very much dependent on the parameters of the structure. So we can do one substitution here. Let's say if we write this as epsilon 33 1 minus delta J. So we have defined earlier what is delta. Delta is the electrical loss tangent, so it's very much similar to damping, mechanical damping, so electrical equivalent of the mechanical damping. And then we have this part. If we just take this complete part and if we call this part as A plus Cj, we can expand this part and we can bring it to this format, A plus Cj. Basically all the terms here, they have some real part and imaginary part, so we can bring it in this particular format. Then if we do the solution, so here this is the capacity part. Then by expanding the real and imaginary parts, we can find that we can explain the earlier observations that we can write this term as y is 2 omega WL by H. Just differentiate between the terms omega and W, and what comes here, we have here epsilon 33 1 minus delta J. So this J we want to take inside, this J we want to take inside. So what we get here epsilon 33 T into delta, and then when we take J inside, so we'll have minus C. So this is the real component, and then the imaginary component will be epsilon 33 T plus A. So this is how we have the real and the imaginary components. So what we find that the real part G is basically delta times epsilon 33 T minus C, and B component is epsilon 33 T plus A. So now we can see why the magnitude of G is so low as compared to the other part B, and why the B part has a dominance of the capacitance. The reason is now very obvious, that in the real part, this is the real part and this is the imaginary part. So in the real part, we have a delta term in front of epsilon 33. So what is the value of delta? Delta is very small, typically the order of magnitude should be 0.01. That's why the capacitive part is very less in the real part. We have the dominance of the other part. This part C comes from the structure. This part C is coming from the structure. So that has dominant effect. But now in the imaginary part, we find that epsilon 33 is directly coming. There is no fractional multiplier as in the previous case, and this has very high value. So we find that the B component is very high as compared to the G component. So the reason is like this. So let us come back to this equation, and let us now input here the values of various parameters. So we begin with epsilon 33. The value of epsilon 33 is 1.28 into 10 power minus 8. The value of delta is very small, and it's typically 0.01 or less. So this is the expression for epsilon 33 T with bar on the top. So T signifies that it's measured under constant or zero stress, and the bar above the top, this indicates that this is dynamic in nature. Similarly, the other parameter is D31. So this is 165 into 10 to the power minus 12 meter per volts. And you recall what is the unit of the permittivity, electric permittivity, that is farad per meter. Then we have the Young's modulus, YE, with bar at the top. Bar indicates that it's dynamic in nature, and E superscript indicates that this is measured under zero electric field conditions. So this is 6.41 into 10 power 10, 1 plus eta j. So what is the unit? Unit is Newton per meter square or Pascal. So we have already discussed that why we have positive here and negative here. This we discussed already in the previous class. So if you now do the multiplication for this part, because we have now D31 also and YE, so if we do this multiplication, we'll find that its value comes out to be 1.74 into 10 power minus 9, 1 plus 0.01 J. So now we can have a comparison of the magnitude of epsilon 33. We have epsilon 33 on one side, and we have D31 square YE on the other side. Now if you compare the magnitude, this is to the power A minus 8, 1.28 into 10 power minus 8, and on the other hand D31 square YE, it is to the power minus 9. So one order of magnitude smaller. So what we find that epsilon 33, it dominates as compared to D31 square into YE. So we have already seen the quasi-static sensor approximation. So quasi-static sensor approximation involves that if we have very low frequency of excitation, typically less than 1/5 of the natural frequency of the piezoelectric patch itself, then we can simplify this expression. You have already done. So if you have not done, then do it again now. And what you can do as an extensional activity, that you can break down the real and imaginary components so that you derive an expression in the form of a plus b j. In the last lecture, we had also discussed how to obtain the resonance frequency of the piezoelectric patch. We had given you homework also, hope you have done. So here we are just recapitulating. So now we are including two things: how to get it theoretically and how to get it experimentally. First, let's see theoretical observations. So theoretically, we just make use of the equation. This equation we have to make use, and here the main term is tan KL by KL. So one L can be added here at the top. So we have this, and then we can add one L in the denominator. So now this tan KL by KL, this tends to 1 at these values when this is pi by 2 or its odd multiple, that is 270 degrees or 90 degrees. So when this angle is of the multiple of pi by 2, under that circumstances we have this term tending to infinity. That means the mechanical impedance tends to 0. So here this term kappa, this is the wave number as we have seen in the previous lecture. So if we input here the values of the piezoelectric patch, I gave you this homework. So by using the parameters of PIC155, which we'll show you in the next slide, you can get an expression something like this: 143 to n minus 1. So all these values, they can be integrated here. So if we input here the value of the kappa, and we substitute omega as 2 pi f, then after solving we can get an expression for f like this. So this is the expression for the first, second, third. All you have to do is keep on inputting here n equal to 1, 2 and 3, something like this. So if you input here n equal to 1, then the first resonance frequency comes out to be 143 kilohertz. Similarly, if you input here n equal to 2, so the second resonance frequency, that comes out to be 143 into 3, that is comes out to be 429 kilohertz. And like this you can find out the higher natural frequencies also. So this is about the theoretical. Now how do we get experimental? Experimentally we can obtain, we'll do this experimentation also in the lab. We have to hang a piezoelectric patch without connecting it, without bonding it to a structure, and obtain its signature using the LCR meter. You will find the peaks. The peaks are at the resonance frequencies. So this table basically shows here the parameters of different types of piezoelectric patches. So here in the calculations which we have shown, we have used PIC 155, sorry, but you can also use the other type, PIC 151 also. So what we can find is there are minute differences. If we see, for example, in the calculation of the resonance frequency of the piezoelectric patch. Resonance frequency of the piezoelectric patch depends on the density. Density is same for both, and it depends on the Young's modulus of elasticity, which is marginally different. So here what we get here, this is the elastic compliance coefficient. So the Young's modulus is inverse of this. So this is the Young's modulus shall be 1 by 15 into 10 to power minus 12 for PIC 151, and for the other one it will be 15.6 into 10 power minus 12. So if you take the inverse of this, you will get the value of the Young's modulus. So we are very much now familiar with the 1D model, where we define the PZT and the structural interaction by means of the impedance expression, that force in the PZT patch is minus z times the velocity at the end of the PZT patch. So this velocity we are measuring at the end of the PZT patch, and velocity how we are measuring in terms of the displacement. So hope that by now you must be very much familiar with the mathematics part. Now we go ahead. So what is the use of this equation, and how do we use it in conjunction with the experimental measurements? The use of this equation is that experimentally we measure G and B. If for example you have done this experiment also, what you get is a signature of the G part and the B part. That is, at each frequency you are measuring G and B. So now you have this equation. We assume that if we know everything about the PZT patch, that is, we know the epsilon 33, the permittivity, we know the mechanical impedance of the PZT patch, we know D31, we know YE, we know the kappa, we know the Young's modulus, then we can very easily obtain the mechanical impedance of the structure. So this mechanical impedance of the structure is obtained from the PZT patch itself. Otherwise, what is the definition of mechanical impedance? Mechanical impedance means that it's the ratio of the applied force to the resulting velocity at a particular point. So that is very difficult to obtain in a true sense. You have to apply force at very high frequency and measure the corresponding displacement or velocity, which is very tough. But here we use the electromechanical coupling principle. Simply we have measured the electrical components. And what are the electrical components? We have measured G and B. So by measuring the electrical components and making use of this equation, we are obtaining the Z. So Z is also a complex term. It has real and imaginary parts. So we get the value of the mechanical impedance of the structure. We need not know anything about the structure. Simply we bond a PZT patch and we can get the value of Z. But the limitation is that this equation is valid for 1D structures only, because this is a 1D impedance model. So what is the problem associated in general? First of all, we cannot use this equation indiscriminately in the case of the 2D structures or 3D structures. Then the other issue is how accurately we know the parameters of the PZT patch, because all our calculations, they depend on the inputs which we are giving here in terms of the electrical permittivity, Young's modulus, D31. So we should know these parameters more accurately. And then the third is the end conditions. The end conditions are that it is a bond layer, but we are approximating it as a pin-pin connection. So let's go into the first two, 1 and 2, how these are addressed. So we go with some of the existing models. Chow, Liang and Rogers, they propose a 2D mechanical impedance model. So considering the 2D vibrations similar to the 1D, and if we can model 1/4 of the PZT patch, just like we have done in the previous case, modeling of the 1/2 of the PZ patch. So if we model 1/4 of the PZ patch, and by following the same principles, they could derive an expression for the 2D case. So this expression, if you see what comes here, Poisson's ratio also comes into picture, and then the kappa is there, but kappa is for both the directions. In the direction x the size is L, and in the other direction the size is W. So both of these come into picture, and then we have a matrix N. What is this matrix? This matrix is this. So we have a very complicated expression, and if you see the impedance in the case of the 1D vibrations, the expression was simple, but in the case of the 2D, the expression is a bit complicated. We have the two forces in the x direction and the y direction, and then we have the direct impedance as well as the cross impedance. So if you expand this matrix, you will find that F1 depends on both U1 dot and U2 dot. So we have the direct impedance and the cross impedance. So total there are now 4 impedance terms. So can we use this equation to obtain these impedance terms? Because what we get from experimentation, we get two measurements G and B. So can we use these set of equations? So totally we have two set of equations, but how many unknowns are there? Total 4 complex unknowns. Each has the real part and the imaginary part. So total there are 8 unknowns. So 8 unknowns cannot be obtained by just using two equations. So that limits the worthiness of the equation. So we have two equations, 8 unknowns. So we cannot use this to extract the structural impedance. Of course, here the force transmission is assumed to occur at the endpoints of the PZ patch only. Now we take you to a simplified 2D impedance model. So this impedance model assumes that the PZ patch is square, and the force transmission is considered to occur at the boundary of the PZ patch all along like this, and the mechanical impedance is defined in a different fashion. That mechanical impedance is basically if we add all these forces, boundary forces in scalar terms, so that gives us a total equivalent force. Similarly, if we measure the displacement on an average in terms of the total area, because now the PZ patch is 2D, it's vibrating, its area is increasing, decreasing, increasing, decreasing. So essentially we define the effective displacement now. So what is effective displacement? Effective displacement is in terms of the change of the area. So area divided by the original parameter. And similarly, the effective impedance is also defined in terms of the effective force. So effective force is all this force all together integration like this. So this helps in deriving another equation. So by using the 2D piezoelectric relations, the direct effect and the converse effect, all we have to do is, if we use these equations in the case of 2D, then we get this kind of expression. So here if we try to understand, what we found that the charge is now a function of both the stresses in the two directions T1 and T2. That's why the two are added up, assuming that D31 and D32 they are same. Similarly, for the strain we have these terms, that we have D31 into E3 will be there definitely, but then because it's case of the stress occurring in two directions, we have the Poisson's effect also. So making use of these equations, this simplified expression is derived. So what is the key advantage of this expression is that here a single complex term, it accounts for the two-dimensional interaction of the PZ patch with the structure. So the advantage here is that from the measurement we have two parameters G and B, and then the two unknowns are also just X and Y, the components of a single impedance term. Like in the case of the previous model by Chow and co-workers, there were 8 unknown parameters, but here there are only 2. So that means now this equation can be used in conjunction with the experiment. Now we show you the experimental verification here. What we are showing here, three different signatures. This black one is the experimental signature. Then the blue signature, like you can see blue signature in both the real part and the imaginary part. I am just highlighting the imaginary part. So this blue signature is on account of the previous model of Chow, and the red signature is the on account of the simplified 2D model which we have just discussed. So what we find is that the models, they have some discrepancy with the experiment. Not just Chow model, but the new model also has discrepancy. Now to take care of the discrepancy, what we do, we try to find out what could be the reason. Now if we compare with the previous comparisons, previous experimental and the theoretical comparisons, previously in the year 2000, Jurjitsu and Zagrai, they had made a model, and the comparison was like this, that there was at least difference of the order of magnitude difference between the theoretical prediction and the experiment. Though the peaks, they were predicted correctly, but then this large difference in the magnitude was there. On the other hand, in the case of the new model, this difference is not that high. So to make further investigations, let us use this to obtain the free piezo signatures, because one of our doubts is that possibly the parameters of the piezo patches, they are not correctly obtained here as inputs. So what we do, first of all, we use this equation to obtain the free piezo signatures. How do we use it? All we have to do is set this term as 0. That is, the PZT patch is free. It does not have any resistance from the structure, so this part is 0. So we get this simplified equation for the free piezo patch. Now we can make one more approximation, that is quasi-static sensor approximation. Under the quasi-static sensor approximation, tan KL by KL will become 1. Okay, so if tan KL by KL becomes 1, then we have further easy equation. So let us now first see for the equation for another extreme case. So for free case, the Z effective is 0. For fully clamped case, it is infinity. So these are the signatures for the free and the fully clamped case. So what we see in the fully clamped case, there are no peaks. All the peaks, they disappear. All the peaks, they have simply disappeared in the case of the fully clamped case, but in the case of the free signature, we have the 3 peaks. So these are the resonance peaks, because at resonance peaks, the mechanical impedance is minimum. So that means the vibrations, they are maximum, and this gives rise to very high value of the current. Similarly, in the imaginary part, we see the comparison. So in the case of the fully clamped situation, the peaks of the PZT patch, they have disappeared completely. Whereas in the case of the free condition, we have the peaks, resonance peaks of the PZT patch very clearly highlighted. So this is the experimental method of how to determine the resonance frequencies. So we'll do this experiment also. Now we do the analysis. So first of all, what we can do is that we can write the simplified expression for the free PZT patch like this. So we have the complex equation, and then we divide it into two real equations, that is one for part G and other for part B. So what we can see is in the G part, we have the delta multiplied to epsilon, as we had said before. So what we have used is that this tan KL by KL, we have substituted it as R plus TJ. This is the substitution for 10 KL by KL. So we can simplify like this. So what happens is that now this is the comparison. Now we see here the comparison between the experiment and the theory. So in the case of the experiment, we have two peaks, whereas in the case of the theory, we are getting only one peak. So what is the reason for this? And then what we find that the peaks, they are not matching also. So these are the two cases, two different PIEZO-T patches were there. So in the case of patch 1, we have twin peaks. In the case of patch 2, we have a single peak. But then the analytical frequency is much less than the actual experimental frequency, which means that in the actual case, there is additional 2D stiffening effect. That's why the frequency is higher in the experiment. So these two observations are there, and now we use the quasi-static sensor approximation. If the frequencies are low, then what will happen? 10 KL by KL will be 1. So these terms, they will vanish. So when these terms, they vanish, we get very simplified expression. For example, for the real part, we get this expression GF is simply 8 pi L square H epsilon 33 delta multiplied by F. So that means under low frequencies, the graph between the G and frequency will be linear, and the slope will be a function of the product of epsilon 33 and delta. Similarly, the expression for the imaginary part will be BF equal to 8 pi L square by H into epsilon 33 F. So that means here the slope of the plot of the imaginary part versus frequency will be again straight line, and the slope will be proportional to epsilon 33. That means if we plot such variations, then from the slopes we can get both epsilon 33 and delta. So this is a way to obtain the epsilon 33 and delta. So these epsilon 33 and delta, we found these values, and they were found to be different from the values specified by the manufacturer. Similarly, delta values, they were also found to be 0.0238 and 0.0225. Again, they are different from the values supplied by the manufacturer. Now, what is the advantage of this? This advantage is that we are now measuring the PIEZO-T parameters more accurately, and we use these measured conditions in the model. We can improve our prediction as follows. So what we do, we first obtain the signatures of the free PIEZO-T patch, and we found that the PIEZO-T patch signature, they are different from the theoretical. So then we will attach the PIEZO-T patch with the structure. So we already have its free piezo signature. So the advantage of the free piezo signature is that we can fine-tune the model of the PIEZO-T patch. So what we do, we introduce here a correction factor. So correction factor is like this, that if we have single peak behavior means that we are getting only one peak, and twin peak means that there are two peaks. So what is the reason of twin peak? Twin peaks, they come into picture when the size of the PIEZO-T patch is such that it's little bit deviation from a perfect square. So while one dimension is L, the other dimension is slightly larger. So let's say this dimension is L, this is slightly larger than L. So that means there will be two resonance frequencies, one corresponding to L, other corresponding to 1.01 L. That's why we have the twin peaks. Now using these updates, compare the plots, because what we have done, we have used these parameters C1 and C2 to shift the theoretical predictions such that they are matching the experiment. So what we have done is we have done this kind of updating of the model of the free PIEZO-T patch. And if you use the updated model, then we get a better set of calculations. Now you see here that the matching is much better. Now to emphasize this point again, I show you the previous results. Now here the experimental and the theoretical ones, they are matching very well. that the slopes are perfectly matching and the peak points are also matching in both the cases. But you will see in the previous case, I am repeating again the signatures for the previous case. Now what you see here, that peaks are not matching and the values are also not matching, and here in the case of the B, the slopes are also not matching. So this was the comparison without model updation, but we have seen in the previous slide the comparison is much better if we do model updation. So this is improvement. So if we don't do updation, we get inferior values and the identification may not be correct, it may have errors. Now we show you the application of the 2D modeling approach. So henceforth we'll use the 2D model only. We'll not emphasize on derivation of the 2D model. If you have understood the 1D model, its derivation very minutely, then the derivation of the 2D is on similar lines. Just we have to use some of the equations, the beginning equations, but rest of the procedure is same. So we are not emphasizing that you derive it yourself, but the 1D model you should be able to derive. Now what we are using is that we are using the term identification. We say impedance based identification. So what is this impedance based identification? Let's say in general the mechanical impedance of a structure has two components, X the real part and Y the imaginary part. For example, if we have a parallel combination of spring and damper, then by using the impedance approach you can find out what is X and what is Y. So here X will be contributed by the damper, so it will be C, and what will be the value of Y? Y will be contributed by the spring and its value will be minus K by omega. So if you try to see the variation of X and Y, because you have the expression, so what we find that the real part is a constant, imaginary part is negative, and this negative value, it reduces in magnitude with increase of frequency. So that means the plot of X and Y with frequency is predictable. X will be like this, that X is constant because this value is equal to C, and then the Y is like this, that is minus K by omega into J. So that means as the omega is increasing, the value is tending to 0 and otherwise the value is negative. So if in general we find that this kind of behavior is there, that means that it is a parallel combination of K and C. Similarly, what we do in the impedance based identification, we try to see the variation of X and Y and then we identify a constitution of the structure. So in general it involves solving the inverse problem. So from the plots of the G and B we obtain X and Y, and then from the variation of X and Y we can identify what are the parameters. So this I am giving you just an example. In general we can have different kinds of variation of X and Y. So this will show you in this slide. So basically impedance based identification, why it is needed? It is desirable in structural health monitoring so that we identify the structure purely from experimental measurements without any modeling. So we make use of the equation, the 2D impedance equation, and solve it to get the X and Y. For example, for this kind of structure, this was a block of aluminium with a PIEZO patch bonded, and here by using the impedance based identification we could get the impedance Z derived. So what we find that if we use model of the PIEZO patch without updating we get some plot, but if we use the updated model we get different plots. So there is a lot of difference between them, so that's why we should update the model of the PIEZO patch before using. So this structure was identified in this particular frequency range 25 to 40 kilohertz as a parallel spring damper combination, and by using the equations we can find the value of K and C also. So how do we find the value of K and C? C is basically X is equal to C. So the value of X is C. So what we find the average value, we say that this is C. And how do we find the K value? Because Y is equal to minus K by omega. So that means K is minus Y into omega. Omega is 2 pi F. So all we have to do is, if we use this equation, then at each point we can find K, and then we take the average value over the frequency range. Similarly, in another frequency range, the system was identified like this. It's a basically a complicated system that we have a mass in series with a parallel combination of K and C, and then there are two external components also. So here also we find that the matching is good, and then this can do structure identification. So what we do, we are drilling holes to induce damage, and what we find that as the damage increases, the K is reducing, mass is reducing as expected, and the damping is increasing. All now we have to do is we have to calibrate these parameters with actual damage, and we can use the field. So in general, we can have a lot of different combinations are possible. So these are some of the standard combinations. So if we see this kind of variation in X and Y, that the real part is constant and the imaginary part is negative, and the negative value is reducing in magnitude, that means it's a parallel spring damper combination. Similarly, if we see that the variation is such that the real part is constant but the imaginary part is positive now, if it's positive and it's linearly varying, then that means it's a parallel combination of the damper and the mass. So similarly, we have to get these plots, and then once we get the plots, we compare with the standard plots, and then we identify the particular system and try to find the values of the parameters, the mass component, the spring component, and the damper component. Let us now see an application of the concept of the identification of the structure impedance for structural health monitoring. So we begin with the fatigue test on a steel joint. In fact, we'll study this in detail when we come to the lecture number 12 on fatigue. We'll study the fatigue of concrete and steel individually, but here I am just using it as an example. So here there were 3 specimens. Each specimen had 3 PIEZO patches which were bonded, and these PIEZO patches were used to monitor the condition of the structure. So these specimens, they were subjected to fatigue loadings. The minute details we'll be covering when we go to lecture number 12. So there were 3 joints. So what you can see that these are basically lap joints, and they were subjected to axial loads in cyclic fashion. So here is a summary of the cyclic loading for one of the specimens, that it underwent a total of 63,586 cycles. So we show it in terms of the cycle ratio. Cycle ratio 1 means that it is the final cycle or the end cycle, and cycle ratio 0.409 means that it has undergone 40.9% of the total cycles till failure. This is the failure mode of one of the specimens. So what we can do is we can use the simple signature analysis, like for the experiment which you have done. You have used the simple root mean square deviation. So what is root mean square deviation? We find out the difference in the values of the 2 signatures, one in the pristine condition, that is before damage, and one after damage. So this difference we do the square and add the sum of squares of all the values at each frequency, and we normalize it with respect to the sum of squares of the original values, like this. So this is obtained in percent terms. So this is one kind of damage quantification, but it is non-parametric. So what we found that if we use root mean square division, we get very confusing results. For example, for one of the patch, the result was like this, that it has some constant value till about 100%, then sudden jump. Other patch we got something that it's constant while the cycles are changing from 0 say about 10% to 90%, there's hardly any variation. And in the third case also, that right from beginning till the final stage there is hardly any change. So the conclusion was that we are getting largely scatter and no good correlation. And then another thing is that we have the three PIEZO patches, patch 1, patch 2 and patch 3, and here are the now patch 1. This is the root mean square division of patch 1. This is for patch number 2. Patch number 2 is here, and this is for patch number 3. So what we can see is that patch number 2 and 3, this is 1, this is 2 and 3. So patch number 2 and 3, they are at same distance from the damage, but we find that the difference is very large. Patch number 2 is giving the root mean square division of the order of 30 to 40%. Patch number 3 is giving it in terms of only 5%. So huge difference and no uniformity. But then use the mechanical impedance approach, we get much better. Like from mechanical impedance point of view, we get result something like that X is constant, Y came out to be negative, and the value decreasing with increasing frequency. So we could immediately make out that it is this parallel spring damper combination, and we could then get the value of the C and K. And here is now the plot of the Y with inverse of frequency. Purposely we have done it. Why we have done it? Because it's the parallel spring damper combination, so the Y part is governed by the spring, so the frequencies is in the denominator. So if we now plot as function of the inverse of the frequency, we get a straight line. And what is the slope of this line? Slope of this line is basically the K. So what we find that as the cycle ratio is increasing, so the frequency with frequency, what we find that the slope of the plot is decreasing, and slope of the plot is nothing but measure of the K. So we have very good results here as compared to the root mean square division. Root mean square division was not showing any change, but using the approach of the identified parameters, we are getting a consistent approach. So this is more desirable. So how do we find, we have already defined that we find K as the average value and C also as the average value. So the PIEZO identified stiffness, we found that it correlates well with the actual stiffness, and it has a much better variation than the root mean square division. Similarly, we show you the example of concrete monitoring using the same model, impedance-based identification. So here also the PIEZO patch, it identified the concrete tube as a parallel combination of the spring and damper, and the values of the C and K parameters, they could be determined from the signature plots. So here is the comparison between the experimental and the equivalent system. So the red is the experimental plot and black is the equivalent plot. So we have good comparison between the experimental and the equivalent system plot for both the real part and the imaginary part of the impedance. Then we subjected the cube to increasing stresses. So basically cyclic loading was applied like this, that we have in the, we applied loading to a certain level, and then in the next cycle we increase, then in the next cycle we increase further, and like this we went till the failure. So in each cycle the stress applied on the cube is higher and higher. So we deliberately chose different strengths, so very wide ranging strengths, so that we get we could test it whether we are getting consistent results for different grades of concrete or not. So what we found that this as we were increasing the stresses, what you find that the modulus, the secant modulus is reducing. The slope of the curve is reducing. That means that the stiffness is going down. So simultaneously we found the stiffness identified by the piezotic patch. So this is the loss in the secant modulus, and this is the loss in the equivalent stiffness, and we found that the two are in straight line. They have good correlation with each other. So the piezotic identified stiffness correlates well with the actual stiffness of the concrete cube. So this can be used for the damage assessment in a more refined way, because we now have the equivalent stiffness. So what I suggest that you can read this paper based on concrete. So it is only a suggested reading, and this will give you more information. Also, what we are going to do is that once you read this, you will receive some data. So what I have done some basic programming, because otherwise if you write your own code it will be tough. So I have already done some programming, and what I will be doing, I will be communicating that MATLAB code to you along with some of the experimental data, so you can use that, and with your own hands you can obtain the mechanical impedance of the structure, and then you can fit some kind of model. So that part I'll send you separately. Also, tomorrow there is going to be one very good webinar organized by MATLAB. So if you attend that, that will be very useful. So I'll be sending the link of that also to you. So thank you very much. Hope this lecture would be useful.